stands for super. Okay, conducting. So you can use a superconductor for SQUID straight away. Okay, and QU is actually a word which is based on quantum mechanics. So it is quantum. Okay, and then we have got I. Okay, so I is interference. And then finally D, which is device. Okay, so all the capital letters are something which is actually nothing but the acronym for. Okay, superconducting quantum interference device. And this straight away gives you the idea that a SQUID is something which is nothing but based on the use of superconductors, okay, to study the magnetic property. Okay, so it's a huge topic. Okay, I'm not going to take up the entire lecture, okay, entire idea, but we are just going to have a small brief on this. We just want to understand the qualitative analysis. So this basically is based on three quantum mechanical effects. You might have studied in your undergraduation, okay, these quantum mechanical effects. So I would prefer telling you this. Okay, the three quantum mechanical effects. Okay, the first one is superconductivity. That's obvious from the name, and I'm just going to give you a timeline. Okay, this is going to be interesting. Okay? And then there is something which we call as the Josephson effect. Okay, Joseph. This is something which I'm going to explain, and probably I'm going to ask you a question on this also. Okay, if I'm asking you one objective question, what is Josephson effect? Please explain. Okay, and finally, magnetic flux quantization. So the magnetic flux that we know, okay, the phi that we know, it is also quantized. Okay, doesn't have a continuous value, and that is also one of the property based on which the SQUID works. Okay? So this is the idea that we are basically going to use. Okay? Let's just have a small look at the timeline. Okay, so let me just go year by year. Okay, and as we see this, we are going to understand certain process that we already know. So in the year 1911, you have already studied about superconductors, I'm sure. Okay, in the year 1911, actually, okay, Kemallam Owens, if you remember, I'm not very name is scientist, but Owens has actually discovered something which we call as superconductivity. He has been credited with the discovery of superconductivity. In fact, the Nobel Prize goes superconductivity. And tomorrow, if we are able to discover a superconductor, okay, which actually operates at higher temperature, if it operates at room temperature, you're definitely up for a Nobel Prize. Superconductors or superconductivity are such materials whose resistivity becomes zero. So if the resistivity becomes zero in a system, that means the loss of energy will be minimum. Whatever electric field you have, whatever heating up effect that happens is basically because of the resistance offered by the system. So in general, when we are using a conductor for passage of electricity, let's say, we use copper. Okay? So copper wire, okay? Or silver. Silver basically more costly, so we usually use copper wire in this home wiring and all. But then there is a lot of loss of energy, okay, because of the resistive effect. Copper is a conductor, still has got some resistive behavior. Certain materials, okay, like niobium, for example, if you just lower it to a certain temperature below 0 degree centigrade, okay, it's around 180, minus 180, minus 200, minus 150, you get the behavior of the material as if it has no resistivity within the system. An electric field will exist forever and ever and ever. Okay? But then it has to be maintained at that temperature. Maintaining a system at that low temperature is again difficult because you have to have additional arrangement. Let's say helium, liquid helium, okay, or liquid nitrogen, okay, and that incurs additional cost. So we cannot have a practical system like that. So what is the aim? The aim is to have a superconductor whose working temperature is higher, that is closer to 0 degree centigrade. Okay, that is much more easier. Okay, that's why this superconductors are actually very interesting property. Okay, if you know this maglev vehicle, okay, mechanical levitation vehicle usually runs in Japan. Okay, basically works on this superconducting. There are a lot of interesting things on these things. Okay, So what happens usually in superconductors is resistance, okay, of so what happened in the year 1911? He observed that the Camerlung ovens. Okay? He saw that the resistivity of mercury when it was actually cooled by liquid helium. So liquid helium can cool further, which cannot be done by liquid nitrogen. Okay? So if we use liquid helium, it can be actually cooled by liquid helium. Okay, uh, and what temperature? It will be around 4.2 Kelvin. Achieving 4.2 Kelvin, it's really difficult. Vanishes. Resistance of mercury cooled, okay, by liquid helium at that temperature of 4.2 Kelvin vanishes. Okay, so this was actually what was observed, and this actually was something which was path breaking, because later on when people started working on this idea, it was observed that there are a lot of applications. Okay, and in the 1957 actually came up PCS theory. Burdeen, Cooper, and Schaefer theory. Okay, and based on this, if you remember your superconductors, okay, there is actually a small part of superconductors in undergraduation also. Okay, it's important. BCS theory is again very important. Okay, it is sometimes repeated in your MSc also. So there is something which is called Cooper pair. So Cooper pair means you are basically having the electrons of opposite spin, okay, combined together, okay, and they move together, okay, and that is the reason that the resistivity of the system goes down, okay, because they can move easily in the lattice system, okay. So this is what is Cooper pair is all about. So what happens is two electrons. Why we are trying to understand this? Because entire logic of SQUID is based on superconductors. So knowing superconductors is important. So Cooper pair means two electrons of opposite spin, okay, electrons of opposite spin and momentum, so they are actually not in the same quantum state, okay, are bound by electron photon interaction. So this is in short, okay. There is a big theory, but then I'm just giving you a brief here. So these are bound by something which you call as the electron photon interaction. If when we go into high energy physics, and I will explain you certain things there, that whenever we are talking about any kind of interaction, be it be among magnetic material, electric material, okay, nuclear material, there is always exchange of these particles. Okay, so in this particular case, the exchange is basically nothing but photon, the photon interaction. In the year 1962, what happened was there was a scientist named Brian Josephson. Okay, now we are actually slowly coming towards SQUID. So Brian Josephson actually predicted, okay, the got deleted or to the previous page. Anyway. So Brian Josephson, what he predicted, he predicts the Josephson junction. I'll tell you what is Josephson junction. We are just going to explain this in a better way. Okay? Josephson junction. Okay. Here what happens is you might actually have two superconductors. Okay, same or different, and you can actually form a junction between them. That junction actually can have a insulator. Even if there is an insulator, we will see that there will be actually an electric field which flows. Okay, so two superconductors coupled by an insulating barrier. Okay, okay. So let's explain Josephson effect now. Okay, and then probably we'll just get back to the timeline. Okay, so let's try to understand this Josephson function. For that, I'll just draw a few figures, and I think it should be clear. So there are different ways of drawing it. Okay, but then let me just tell you this. So let's say I have got two superconductors. Okay, why two? Because I'm separating this superconductor by a bar. This is the separation, and this actually might be an insulator. Okay, so this is a superconductor or not. Just writing it down here. Not semiconductor. Okay, please write superconductors. Many of us do this mistake when we write down or explain superconductors. Somewhere we write down semiconductors unknowingly. Okay, we have that habit. And you know this superconductor will have Cooper pair, and then this is an insulator. This is basically nothing but a junction, we can say, and mostly it's an insulator. Okay, this is a junction. These Cooper pairs actually will actually cross this junction, okay, and go to the other side. So that means there is a field which is acting between this end and this end, which gives enough energy for the Cooper pair to actually cross the junction. And this not only happens from this side, it will actually happen from this side also, obviously, because this is also, you know, superconductor, right? So it will actually do this. So what is this? This is basically nothing but a quantum mechanical effect. That is basically, in general, we can say it's a quantum mechanical tunneling. Okay. So whatever current we have because of this Cooper pair, we basically name it as critical current. Okay. So this critical current, okay, depends on three factors. Okay. Number one, size of the junction. Size of junction. So I'll explain what do I mean by size. In simple words, it means that how thick is this junction. If this junction is around, let's say, 1 centimeter, this is not going to work. If this is around 1 nanometer, this is going to work. You have to understand that this size plays a very important role. Okay? Size of the junction. Number two, what is the superconducting material? Okay, what kind of material we are using? Superconducting material. And finally, it will also depend on the operating temperature. So, you know, superconductors can only work at a certain temperature range. Okay, so depending on the material, you will know what is the temperature, and based on this, it will work. So this is the current on which this depends, Josephson junction. But then let's see what is exactly Josephson effect. Already you have got a brief idea here, because I say that even if the superconductors are separated by an insulating part, they're still going to have a current which actually will flow. That means we're basically going to get a current flow, okay, or we are going to have an electric field, okay. So if I just want to write this down, okay, probably I can say it happens both in AC and DC, okay. So a direct current, I'm talking about a DC Josephson effect now, okay, flows across the Josephson junction. Look at the diagram above, and then you can see that there is actually a Josephson junction. Flows across the Josephson junction in the absence, okay, of any electric field. So direct current will flow across the Josephson junction in the absence of any electric field. So that is how it's done, okay. But then let's just have a look at it in the form of a diagram. Okay? So this is critical to the understanding. So we'll just go probably. Okay, let me just draw one diagram here, and then maybe you can also try. So maybe this is a superconducting slab, okay. Not that wouldn't go. You can go even better. So let's say this is basically a slab, a superconducting slab, okay. And what I do is usually I will apply a potential across it, okay. And let's, and since I'm talking about a DC effect, so I'll just apply a battery here, and then connect across the two ends of the superconductor. And this superconductor is, let's say, kept at certain temperature, okay. And now what happens is, if we are going to apply a potential, okay, you are going to get a current flow. Okay? And then, you know, if it's a superconductor, the current flow is going to be maximum. Okay, whatever is there across this superconductor, you are not going to have any kind of resistive effect. How do you know? We can simply connect a voltmeter. Okay, you can simply connect a voltmeter across it, maybe here, maybe here. Okay. Now what happens is, if we're basically connecting a voltmeter here, and if it's a superconductor, what we expect that this potential drop is going to be zero. There is not going to be any kind of potential drop because there is no resistance. Okay, the potential at this and this point was going to be more or less the same. So there is no potential drop as such measured across this superconductor. Okay, so this is the simple idea of a superconductor. Now, what happens in Josephson effect is, okay, maybe I can just go this figure again. Okay, so what happens here in Josephson effect is, we are not going to have a continuous superconductor. We are basically going to break it into two. Okay, might be of a different material, it might be of the same material. Okay, that's not relevant right now. So let's just break this into two. Okay, try to make a better diagram. Okay, so I've broken up into two. Okay, I'm just doing the 3D effect here. I've broken this up into two. Okay, might be a different material, it might be a same material. Okay, and then what I do is I connect the same battery. Okay, and then let's say the distance between these 2 points. Okay, the distance between these 2 points is, let's say, 1 centimeter. Okay, and now when we actually measure the voltage, let's say this is 5 volt, and when we actually measure the voltage across this, we are going to get 5 volt. Why? Because it basically doesn't have a path for the charge carriers to flow from this end to this end, because this is separated by a distance of 1 centimeter. Okay, so that means this is basically acting like a normal big broken system. Okay, it's basically an open circuit system that we are talking about. Okay, but let's say I have not considered this to be 1 centimeter. Okay, I'm just taking it to be 1 nanometer. So the distance is very small. Okay, so if I just take it up to be 1 nanometer, okay, and now I can put an insulator in between as well. Let me put out an insulator, dielectric material maybe. Still, I will see that this will remain as 0 volt. This will still remain as 0 volt. This will be 0 volt. So that means charge carriers have been okay. So this is basically nothing but having an electric field developed between this edge and this edge, as a result of which do have a current which actually flows through this junction. Okay, so this junction that we actually have is basically called as Josephson. So I'm just explaining this, okay, because this is something which is not very usual. We need to understand this when we study superconductors. So this is your Josephson junction, and this is basically what we call as the Josephson effect. Okay, so that's there. So see, I'm not writing down any sentences for this. Just have to understand that if we are reducing the distance, it will basically be enough for the voltmeter to show 0 volt. So there will be a Josephson effect. We'll still have the current actually flowing across this. Okay. So this is your Josephson effect. So if you just go into the timeline, 1962, Josephson actually have predicted this, and this is what we are explaining. Okay, I think this is important. So I'll just explain this. And then what happened is, in the year 1964, the SQUID came into the picture. So now we have the year 1964. So in the year 1964, SQUID was discovered. I'm just not giving you the name of the scientist. You can always find it out. Discovery of SQUID. Year and timeline might be important for this particular question, okay, because we are not going too much into the details of the physics behind, except probably the Josephson effect and so on. So in the year 1986, but even if the magnetic field of super or the behavior of superconductor was used to understand the magnetic property of certain material, it was a costly affair because still it's costly, but then at that time it was super costly because you have to lower down the temperature to a very low value and then you can actually have a superconducting behavior and so on. So what happened with time is people tried to discover high temperature superconductors. Okay, one of the important high temperature superconductors, okay, which was actually discovered in the year 1986. Okay, it was actually working at around 30 Kelvin. Okay, so this is at 30 Kelvin. Okay, initially 1911 superconductor 4.2 Kelvin. So 30 Kelvin actually was a good change. Okay, and these are nothing but certain ceramic materials. Okay, which actually basically will work. Okay, and this was actually a copper-based material. Okay, copper oxide to be perfect. Okay, copper oxide. So these are actually nothing but ceramic cuprate. Okay, oxide. Okay, and what it did was it actually used liquid nitrogen. Okay, it was using liquid nitrogen and not helium. Use of liquid nitrogen. So if you want to go to certain minus temperature, you can use liquid nitrogen. If you want to go below that, you need liquid helium. Okay? So liquid nitrogen could be used. Okay, instead of. So when people you see around that people are actually continuously synthesizing new samples, new materials, okay, and sometimes being not too scientific, we wonder what is the use of discovering so new material. Okay, we have to see that every material has got some specific application. Okay, so that is what is happening. I will give you just recent news. Okay, recent news in the year 2019. Okay, Max Planck Institute. Okay, one of the best in the world. Okay, also have they are also working on the superconductors, and please remember this uh, theory is there, but then these are pure experimental work which is actually doing some path breaking research. Okay, they basically demonstrated superconductivity, okay, in lanthanum. Okay, this is a rare earth material, lanthanum hydride, at 250 Kelvin. 250 Kelvin is quite a lot, right? It's quite high. Okay, it's actually just minus 23 C, and there are degree centigrade. Okay, and there are places in the Earth where the temperature will be even lower than that. You take a place like Russia. Okay, there are a lot of cold places. Take a place like Iceland. Okay, some places in US. Okay, the temperature goes that low. So there you in fact don't need anything to actually have a superconducting behavior. And this is actually path breaking. Okay, but these materials which has been synthesized, they might have been synthesized using certain technique. If you use lanthanum hydride using some other technique, probably this won't show that behavior. Okay, so this is also something which is path breaking, but at the same time, this is all in the uh, discovery. Okay, this is a discovery which is actually probably in the changing stages. Okay, it's basically nothing but in the stage where people are trying to understand it better. Okay, so the people are still working on this. Okay, so but one fine day when it starts working, probably this is going to be more part of it. So when you read your book, okay, and try to understand certain topics, you realize that okay, I know about this. Okay, and then probably you are very confident that this is correct. But sometimes uh, we'll see that when we look into later discoveries, it is observed that whatever we have studied is nothing but uh, half knowledge. Okay, I'll give you a very simple example. If you ask any undergraduate student, even if you are thinking neutrino, neutrino is something which is massless. Okay, this is something which you have studied to date. But let me tell you, neutrino is not massless. When we do our course on high energy physics in your fourth sem, I will give you a lot of experimental observation based on which it was seen that neutrino is not massless. It has mass, but very difficult to detect. Okay, there is something which is called neutrino mixing and so on. Okay, so similarly, in a way, we can say superconductors. People have not seen this discovery in 2019, and whatever we have in our book is all based on something which has been probably known till 2010 max. Okay, if we don't have a newer edition, we don't have that information. Okay, so that is why it's important to actually look into the internet and find out new discoveries, so that whatever we study is actually complete in every sense. Okay, that's very important. Let me just finalize this idea on SQUID. Okay, and what exactly we do with SQUID. Okay, I think we already have an idea and how what are the principles that we should know to understand how a SQUID works. It basically measure. Now using a VSM you can actually measure the magnetic change, magnetic field in a system, in a sample, and that measurement might be will have some range. Okay, it's like if there is a very minute change, it might not be detected by VSM system. For that, we actually can use a SQUID. So to measure extremely small, okay, weak signals. So if we have a very weak signal also, that can also be detected. Okay, such as now if you imagine a human body, okay, we know that we do have some current pulse flowing in our body, and because of that we do have a magnetic field. That magnetic field which is created by you and me is very small, okay, but these small changes actually can be detected. Okay, so these changes in human body. Okay, or we can just write it down: human bodies electromagnetic energy field. Okay, so electromagnetic energy field changes in the human body can be detected, and I think you can straight away guess that this will definitely have some medical application. Okay, if you are basically it's actually used also. Okay, so if you are basically going to have any kind of heart disease, okay, and if you can change the measure the change in the signal, the slightest of irregularities in your heartbeat actually can be measured, and such techniques can be actually used. Okay, it has got such applications. Okay, and what are these superconductors made of, based on which we are actually having the SQUID device? Okay, it's either made up of a lead alloy. So there are certain alloys which is combined with lead, which actually show you the superconducting behavior, or even we can actually use niobium. Niobium is a very good magnetic material. Okay, so it's a very good magnetic material. Okay, so one of the strongest magnetic material in fact. Okay, and if you look into the SQUID, there are two types. Okay, there are two types of SQUID. Okay, I whatever effect I mentioned was actually based on the DC signal. Okay, there is also something which is based on the RF signal or the AC signal, so radio frequency. Okay, so SQUID. Okay, RF SQUID. Okay, and this RF SQUID is basically made up of one Josephson junction. It is made up of one Josephson junction, and since it is only one Josephson junction, this is less sensitive. Okay, so it depends on the application. I can actually use a system which has got two Josephson junction, and that is basically nothing but a DC SQUID. So if you just look into a DC SQUID, when you write down SQUID, please make sure you write down all in capitals, okay, because of the acronym. It's basically a double junction, okay, junction and mode sensitive. This double junction which actually plays the role of quantum effect. Okay, so what happens usually in a double junction is, okay, give you a brief. You have a current which is I, okay, and let's say you have actually designed two junctions of a superconductor. So let's say we have got this, and you have divided the superconductor into two parts. Okay, so let's say this is one junction, and you know superconductors no resistivity. So whenever you have the current, you will actually have a current I by 2 flowing through this, and you have an equal current I by 2 flowing through this. Okay, and they will actually have interaction at this junction. Okay, and then finally they will cross over. Okay, you will have the current, final current here in this end. Okay, So this is how a double junction is basically constructed. Okay, so the in the absence of any kind of magnetic field, this input current will split into two, I by 2 and I by 2. Okay, now if we actually apply a magnetic field, okay, maybe I can just write down this sentence here. So what happens is that in absence of external magnetic field, okay, the input current splits, okay, into two branches. Basically split into two branches. And then what happens is I can actually apply a magnetic field, okay, I can actually apply a magnetic field, and then I will see, okay, now if small magnetic field, where do I get that magnetic field from, the small magnetic field? It can be from the sample that we are talking about, okay. If it has got a magnetic property, that magnetic field can be supplied by that sample, okay. If a small magnetic field is applied to a super actually proportional, okay, this phase is proportional external magnetic